Hey there, everyone. This is Propaganda Panda, aka Omar, not the other Omar, but the younger Omar. And this is going to be our first session of the Jungle event for the training, the Red Team training. And I am very happy to announce that we have Georgia Weidman here, who is currently working on version 2 of the Red Team. So, very excited to have her here. Thank you all for being here. And please, of course, since this is kind of like our first time doing this, we're still working through some technical difficulties. So we do appreciate you all having some patience with us. Feel free to give us feedback as well. We have the Discord server here. If you look at track 1 Red Team, if you could put questions there, if you need help with anything, I'll be monitoring that along with Travis here, and we'll be working through that with you all. And Georgia, if you don't mind, let's go ahead and get this thing started.
All right, thank you. Hey everybody, it's Georgia. The notorious. So actually the book that I'm working on version 2 of is Penetration Testing: A Hands-On Introduction to Hacking. And in Portuguese it is Testes de Invasão. Oh, you guys can't see me. I'm like holding up the books and you can't even see me. Probably for the best. All right, so we're going to talk a little bit about exploit development today. If you want to pass your OSCP from OffSec, this is a really great place to start. But are you going to come out of this being able to like bug bounty on the iPhone? Probably not. It takes a little bit more than 2 hours, but we're going to start at the beginning and kind of work through some of this stuff. I know it was brought to my attention that I copy and pasted some stuff that said that I was going to give you guys VMs, and I will. It will be emailed to you after the class. I don't know. Blame it on the pandemic and blame it on the fact that things are actually going very well in the version 2 of penetration testing. I get about 10 messages a day asking me when version 2 is coming out, and to that I cannot say, but a real I guess stopgap for it was, and I've said this before, but so I really wanted to have an online lab because I get probably 20 messages a day about setting up lab stuff, and if you've done my book, the lab did not age as well as I had hoped. So my big thing was for version 2, I wanted it to be like all online and have like the ability to do like extra exercises afterwards and all that. And after many failed attempts at getting that, I finally like have the right partner for that. So the stars have aligned and version 2 is coming imminently. So tell your friends, because that's your insight for being here, is that all is well in the world and version 2 is going to come a lot faster than I previously expected. All right, so I recently did this class, and different class. I'm doing it again on July 1st, but it's on reverse engineering, kind of the same sort of intro. And they gave me all this feedback, like shut up and just teach, and whatever. But that's difficult, so bear with me. There are going to be asides. We're working on it, making me like stay on track, but it may be I take some asides. Some people like it, some people don't. I don't know. That's just me. I am what I am, I suppose. All right, so it probably also said in the description that I was going to use updated VMs, which I'm not, because again, as they say, we're in pandemic mode. I am way behind where I need to be in life, but I'm keeping up to date on version 2 at the very least. All right, so you will get these VMs after class. They'll send you an email. My apologies on that. I know some of you would probably like to work along with me. Um, blame it on the weatherman, I guess. I screwed that one up. Okay, so it's, the usual, Cali, and which another insight that literally nobody knows is that I'm actually dumping Callie and Parrot and all of them for second book because it's the biggest problem because they keep taking down their repos. So it's gonna be a custom like distro kind of thing. But there will be like it'll all be mentioned. But I just don't want it to be like it was this time. So I mean there's if you ever been to an airport, people are like, oh, Windows XP isn't still around. But this is really just the same as everything else, in terms of like exploit development. And then Ubuntu's also old. The fact that these VMs are old like has nothing to do with the exploit development portion of it. We're not actually attacking the operating system. So yeah. Okay, for when you get these, the password on both of these VMs is password. Yeah, I know, but don't do as I say, not as I do. Don't use the password. And for Kali, this is actually like a custom Kali that I made for the book, but you can, if you have an updated Kali, you can use that as well. Some of the tools probably will have changed because they do. Like Metasploit in particular seems to like never be satisfied with things like MSF Venom having the right tag. And you don't even have to use Kali. Like if you have like Pen Tester's Framework or anything like that, or Parrot or whatever all the other ones are called, it doesn't have to be Kali. We don't actually even use it that much. But anyway, all right, moving on. Actually getting started. All right, so I even have slides. I'm not entirely sure what was in my head with my like black with like bright yellow green writing, but you know, meh. All right. I don't use slides very much, and you probably will not see slides very much in this class. However, slides can be made available to you. The slides do walk through everything. There are write-ups as well. I'll just send it all to the organizers at the end, and you guys can use what works best for you. Personally, I don't like slides. I like write-ups a lot better, but some people like slides. So we're gonna do a little bit of slides and a lot of hands-on. So this is a really like basic, and if you guys have a computer science degree or something, you're probably like, oh, you're missing a lot of stuff. And you're right. But this is a really simplified version of a program in memory. So where we're going to be focusing on today is this bit down here at the bottom, the stack. That's certainly not the only place you can have vulnerabilities. I mean, default passwords are a vulnerability, configuration issues, there's heap. You see the heap up here a little bit higher. There's certainly, you've heard of heap-based overflows. I mean, there are tons of different kinds, but particularly if you want to pass OSCP, theirs is a stack-based overflow, and it's the best place to start, I think. So that's what we're gonna do today is focus on the stack. The best outcome of this would be that one, it gets you ready to do OSCP if you want to, and two, it is a jumping off point to learn more. I have found, and again, here I am being tangential, I found like when I was starting out in security that there was, and it's certainly gotten better. There's a lot more resources for beginners now, but it was like there was so much knowledge assumed that once I got this basic stuff kind of in my head, I was able to like understand a lot more, but there really wasn't anything that like explained this sort of stuff. Anyway, tangents. So again, we're going to focus on the stack. What you might notice from this picture is the stack is like backwards, and I would really like to go back in time and like be at that meeting when the founders of computers decided this was a good idea to like have the heap grow one way and the stack grow the other. I would really like to be there, but unfortunately I probably wasn't even born, and probably neither were you, most of you. So anyway, so you see the stack grows from, so we see high memory here at the bottom and low memory. And if, memory is that thing that when like the beach ball on your Mac or like your Windows freezes up, it's probably because like it's a memory issue. It's where your computer like stores stuff, which I realize is a silly definition, but the like deep details, I mean, pick up a Windows internals book if you really want to know, but that's some hard reading. Anyway, okay, so high memory to low memory, which is going to come into play, certainly. It's just backwards. Just remember it's backwards, and it makes no sense why they did it this way. I mean, there's the text section is like where the code is, but basically, yeah, we're going to be focused on the stack. So this is x86, which you might be like, x86, come on now. But there's actually still, especially if you're working in like IoT space or some of the phones even still are 32. But again, it's a good place to start. Things get more complicated as you go farther. Some of you might be mobile people and you want to do ARM. ARM is actually very similar to this. It's just, I mean, I think it's more similar to this than it is to 64-bit, honestly. But you know, things are going to be a little bit different based on your architecture. I mean, this is Intel 32-bit. 64-bit gets a little more complicated, and ARM is just a different set of registers. Basically, what things are called and like where stuff happens to go will depend on your processor. But you know, the general principles of we have registers in our CPU and they do things and stuff happens is universal. So if you start out here, it'll be, I think, a lot easier to pick up one of the other ones. So general purpose registers. So registers are, you know, I said memory was a place to store stuff. Well, registers are another place to store stuff. Remembering from my computer science degrees, I think registers, really the whole point is that it's faster. Like pulling stuff out of memory is like takes, you know, 1 gazillionth of a second, but pulling it from the registers, which is actually on the CPU, is faster. Which, you know, computers are so fast these days, you probably wouldn't notice, but I think that's what they said in computer science class. But anyway, just think of it as another place to store stuff. So for x86, and again, this will change, like in ARM, they're just like R1 to a million. In 64-bit, the E turns into an R. That's not right. R is ARM. I don't know. But anyway, but before there was 32-bit, which again, I'm probably talking like way before any of you guys were computing. But there was 16-bit, and before that there was even 8-bit. So actually all of these were just like, instead of EBP, it was BP, and then they just put the E on it to make it extended base pointer. So, you know, wait until we get like 64 times 2. All right, so the ones we're really going to focus on are actually just these top 3. These are going to be our interesting ones for us, but there are others, as you see. So anyway, the most important one for us is EIP. That is the instruction pointer. That is going to hold the memory address, the address in memory of the next instruction to be executed. So taking that into account, you might understand why control of EIP is our ultimate goal. We want to get code execution. We want to take over this machine and make it do stuff that we want it to do. And being able to control EIP sounds like a really great way to do that. Is that the only way to exploit things? Absolutely not. But it's a good one. So remember, that's the memory address. It's not actually like, EIP isn't going to have like startcalc.exe to start your calculator in it. It's not going to have the actual command. It's going to have the memory address of the code. So that will certainly come into play. The other two that are really interesting to us, since we are playing with the stack, are ESP and EBP. That's basically the top. ESP is the top and EBP is the bottom of the stack. Remember that the stack is upside down though, so actually EBP is going to be at a higher memory address than ESP, even though ESP is like the top. And you'd think things would grow and get higher, but no, they get lower. Again, there's other ones. We will probably see some of them come into play, like places to jump to, but really all you need to know is EIP, ESP, and EBP for now. Again, instruction pointer, that's what we want to get control of. ESP and EBP are going to be our boundaries for our stack, and our stack is, since we're doing a stack-based overflow, this is probably a good thing to look at what's going on in the stack. So again, you will get these slides, and you know, all right. This is also a problem that I have, despite the fact that, like, I know these slides. I will always tell you everything that's on the next slide, before it happens, but actually, I guess I didn't really, but usually I do. But just watch out for that. All right, the stack, it is first in, last out. So I like to think of that, I guess, because I'm weird that way, as like a stack of lunch trays, which we don't have lunch trays anymore because pandemic stuff, but say we did. All right, so many of you probably remember lunch trays. So, when someone stacks up the lunch trays and you come to, they're going to put like the first one on, and that's going to be at the bottom. They put more and more on, but then when you come through and take one off, you're not going to get the one at the bottom that was the first one that was put on. Instead, you're going to take the one on the top. So, again, if you have a computer science background, like if you took computer science classes with all the theory and stuff, this is, oh yeah, one of those. Because there's different stuff. But yeah, the stack first in, last out. So first thing that goes in is going to be the last one. Same with lunch trays. That's how I like to visualize it. Some of you may be beyond that. And again, we saw this already, but it grows from high to low memory. It seems upside down. 2 instructions, which this is not a coding intensive class, because in addition to everything else, you're also going to get the exploit skeletons. So, a lot of classes, it's like you have to learn how to write basic Python or C or whatever. That's a completely different chapter for me. I'm going to give you guys the exploit skeletons. All you have to do is fill in the exploit, being able to connect to a port in Python or Ruby or whatever, do that if you want to, but I'm going to just make that available to you so you can just focus on the exploit. So again, not a coding intensive class. You might see these push and pop instructions like, oh God, we're going to have to do assembly and stuff. But no, these are actually well, not the only, but most of the assembly instructions you will have to care about. So don't worry if you don't have a reverse engineering and assembly background, not an issue. So just push instruction, it puts data on the stack. So you can think of push as somebody putting something onto the stack of lunch trays. So they're refilling the lunch trays and they put one on, they would use a push instruction. And likewise, we have the pop instruction, and that's going to remove data from the stack. And it's going to move it into one of those registers. So, it might put it in like ESI or EAX. It goes where it wants. So it'll push it or onto the stack, pop it off the stack. So you can think of the stack kind of like scratch space. It's like room to do what you need to do in the program. Like if you're doing calculations, if you need to like save something, like just a scratch space or something. Local variables go here. So yeah, you can do whatever you want with the stack, which is part of the problem, but push and pop is really all you need to know. Putting things on and getting things off. All right, so here's like a stack frame. So every function is going to have a stack frame. And if you code anything like me, you'll be like, well, I just really just see, for Java, for instance, everything's an object. I just like open an object and start scripting inside of it. It's bad. Something about my brain just doesn't do object-oriented programming naturally. But even still, like if you just write a program and it just has main, and going back a couple main. So if you guys have not done C, more power to you. Stay very far away from C. I'm just kidding, because most things are still unfortunately written in C, like the operating system level. So, but anyway, in C and some other programming languages, like the first function that's called is always called main function, and then it calls other functions. So, when the program starts, main will get a stack frame. And even if you're like me and you don't use functions as much as you should, there's still going to be like stack frames for built-in functions. Like, if you want to print out text to the screen and see, there's like 12 different functions that do it. Stir copy is one we're going to see. Well, that's copying data. But there's a lot of that, but you're not going to write like the basic input output of life yourself probably. So you would call like a built-in function that C already has, and then that would have its own stack frame. So even if you just open main and just script stuff, you're still going to have other function calls in there. Notice ESP at the top at low memory, and EBP I probably wrote this in Word, but EBP, like, it's actually supposed to be right at the bottom, and I'm not sure why it's not. And again, high memory at the bottom, so EBP is going to have a high memory address, and ESP is going to have a low memory address. Our memory addresses are all like hexadecimal stuff, but again, we're not going to worry about all the theory. We're going to just make this work. Okay, calling another function. Again, this is going to happen even if you just do one function. You'll call built-in stuff. So main will call another function. So somewhere in the middle of main, we call like another function of ours, or a built-in function. But when it finishes executing, so we called something like prints out hi, hello world, or whatever to the screen, but then it finishes executing, you don't want to start back in the calling function like at the beginning. You don't want to do all that. You want it to pick up right where it left off, right? So in order to pick up where we left off, obviously we need to save where we were so we can get back there. Because we don't want to start at the beginning of main. We want to come back where we started. So this is going to be a little different based on your platform. Really, I should just do everything in ARM now because it's the way of the future. But these calling conventions may be a little different if you're looking at another platform, but I mean, they ultimately accomplish the same thing. So the goal being able to seamlessly go to another function and come back and pick up where we left off. So for x86, what happens is before we hand over control to our called function, it pushes its return address onto the stack. So before it leaves off, it just takes like where it needs to come back to, it pushes it on the top of the stack, and then it starts up the next function. And if it does, oh, that looks awful. If that doesn't make any sense, you're probably not the only one that feels that way at this point. That picture did not turn out the way it was supposed to. But whatever. I'll fix it before I send it to you. So we still have main stack frame. You can see most of it. So it has main stack frame, that return address, the place that we want to pick up. This is where execution will continue after our function finishes. Some of you might be thinking, well, if that's the address where things will continue executing, getting control of that might be really cool. And you are right. And you are thinking absolutely in the right direction. We want to think about ways that we can take control of this thing. If it's just going to, because it was told in its, early days, to take this return address and execute, absolutely controlling that would be awesome. So EBP and ESP are now in function 1 stack frame. I know you can't see the top. ESP and EBP point to the bottom and the top of this currently executing function stack frame. So when we're calling, I call it function 1 here. When function 1 is executing, EBP and ESP will be in that stack frame. Remember, the stack grows to low memory, so those will be at lower memory addresses. But what's really, really interesting to us is there's this return address just sitting here. And this is where I really wish I was there when they thought this would be a good idea, because remember, the stack frame grows up. So we're growing up towards function 1, but if we copy data into it, the data goes down. And thus stack-based overflows were born. So I don't know. They probably weren't thinking about security. Nobody was back then. It never occurred to anyone that this was going to be what it is now. All right, a couple things. As I said, we have to walk before we run. There are a few things that I've actually turned off. Actually, probably just one in this case. So you may have heard of address space layout randomization. It says we will study this later because this are slides from 2-day class. Silly me. But there are certainly ways to bypass address space layout randomization. Sometimes it's easy, sometimes you have to do like a memory leak, but again, we're gonna walk before we run, and they don't do ASLR in the OSCP, at least as of now. And so what ASLR does is it randomizes locations in memory. So if we want to if we want to write an exploit and we want to hard code in like a memory address that we want to jump to, address space layout randomization was basically created to stop that, to make it difficult, if not impossible, to know where things are going to be in memory. So there's certainly a lot of other anti-exploitation techniques you will run into in your continued studies. But for now, basically, I'm just pointing out that I've turned address space layout randomization off on the machine we're going to use. So it's off. If you have your own like Ubuntu VM and you kind of do the same thing and you're like, why is this not working? It's probably because ASLR is on. I would again encourage you to start like without all the stuff, if you will, the data execution prevention, the stack cookies, all. I mean, there's tons of stuff since the beginning of buffer overflows that people have put in place to try and stop this stuff. But that said, that's really up to the developer to use that stuff. You may find, particularly again, I keep harping on IoT, but like IoT and like inside like the embedded chips, like people have done a lot of research on like attacking like the chips. You see stuff like the Wi-Fi chip getting hit, or the Bluetooth chip, or the mobile modem. So it's great remote code execution because it just broadcasting itself, but a lot of that stuff like doesn't have a lot of the latest and the greatest in terms of exploit mitigation. So you might be surprised, you might actually be able to find some instances, especially now since everything's moving to IoT, where a lot of this stuff doesn't exist anyway. So yeah, here's how to turn off ASLR. Yes, I use Nano. I know that's a controversial thing to do, but you try teaching a class with VI. I dare you. You make one mistake, it just cascades. Nano is my go-to for when I have to do it online. Who's calling me? So yeah, this is more for you. This has already been done in the VM, but again, if you want to do this like in your own VM, and you're like, why is it not working? This is probably why. All right, so back to where we were. So returning to main. So function 1 finishes, it needs to go back to main. So basically function stack frame is unwound. So function 1 is done. So it's gone. Its stack frame goes away. ESP and EBP, they're restored to main, or the calling function. And that saved return address is loaded into EIP. What was EIP? The instruction pointer. Remember, EIP is the memory address of the next instruction to be executed. So that sounds right? Our goal was to save the next instruction in main to be executed onto our stack. And now when the function is finishing, that saved return address from our stack is loaded into EIP. So that sounds like I actually might know what I'm talking about, because things work out the way they should. So execution will continue where it left off. It won't start at the beginning of main or anything like that. It'll be like it never left, and everything will be good. But again, you can maybe see why getting control of that saved return address, which is then loaded into EIP, might be a good thing to take control of, because it's going to go in EIP. And I said at the beginning, getting control of EIP, that's code execution, and we like that. So definitely getting control of that saved return address would be a good thing for us to do. All right, vulnerable code. So this is on your Ubuntu machine, which you probably don't have yet, but it will be on the one that I give you. So this is really, really basic. So sometimes you're going to have source code. There's a fair amount of open source things, so certainly you can, one way to look for vulnerabilities if you have the source code available is to look at the source code. This is a very basic program. If you don't have the source code, you can just mess with it. So try and there's this thing called fuzzing that we won't get to today, but basically sending bad input to programs, or just as much input as you possibly can. Try different stuff to see what happens. I'm only half joking when I say that the reason I've done well as a pen tester is because I can't follow directions. Because if you're supposed to use a program a certain way and I do something else, and the person who wrote it didn't think about the possibility that someone might do that, the program will probably act in unexpected ways. If any of you guys have a programming background, if you don't do your try catch blocks and stuff like that, and just stuff that doesn't work out the way it should, weird stuff can happen, and attackers like weird stuff to happen, as we'll see. So as a developer, I realize this isn't a secure development class, but as a developer, think, if you're ever building anything, think with the attacker in mind. Like, what is an attacker going to do to mess with this, and how can I stop it? Because I think a lot of people, including myself at times, are really, laser focused on getting the program to work the way it should, that, we don't worry about what if somebody sends in a bunch of crap instead. But anyway, side noting again. All right, so this is just a really basic C function. Well, not function. There's 3 functions in it. C program, and it's, again, I said you don't have to learn any programming, and you don't, because I'm just gonna walk through this real quickly. So you see we've got, so the include statements, those are just C libraries. So we have, let me get this moved over. If you're a Python person, this is gonna make you scream, because Python is based on indentation. C is not, it's based on brackets. You see the brackets. So we open and close functions with brackets in C. That's just how they decided to do it. But you see we've got 3 functions. One is overflowed, one is function 1, and one is main. As we said previously, main is where everything is going to start. So despite the fact that it's on the bottom, that's what's going to get called first. If we look at main at the bottom, we see it's got weird stuff in parentheses. So that's where the arguments to a function go. So if you need to pass something to a function, you put it in the arguments. Like if it was a function that said hello and then your name, I think that's how, at least in my day, which makes me sound old, that's how we started programming. You would do a program that said hello world, and then you would do a program that said hello Georgia or hello John or whatever, based on the input. So if it was something like that, you would pass the name to say hello to in the arguments. But this one actually looks kind of weird. It's int arg c char star arg v, and then what are those even called? Braces. But what that is, that's just C jargon for command line arguments. Input from the user. Input from the user is a great place for attackers. Input from the user is a terrible place for security people. I mean, you look at I do some web application stuff. Web application is really big right now, obviously. But the whole problem with it is that users can input things. If users couldn't input things, I feel like security would be a lot easier. But anything that you don't control, that the user controls, is potentially trouble, because the user might either be incompetent or they're an attacker, which you might be surprised how often those are exactly the same. Like I said, it's only half a joke that, I can't pay attention to instructions, so I end up crashing stuff. It's oh, cool, it's vulnerable. All right, so inside of main that takes command line arguments, the first thing we do is call function 1. Function 1's up here, and it takes as an argument argv1. So that is going to be the first command line argument given by the user. So your first question might be, what if the user doesn't even put in any input? What's going to happen then? But though that's a good question, that's not the one we're going to focus on now. Where we call function 1, and function 1 is up here. So naturally, the next instruction to be executed, which is this printf thing that says executed normally, this is going to output to the screen executed normally. So what that's going to do is save the address of this, or the assembly to go along with it, on the stack, just like we saw. So it's going to be, right here, return address, and call function 1. So what did I just do? So now we're up in function 1. It takes char star. So strings and C are not friends. So strings, like the word Georgia, are actually character arrays. So it's like GEORGIA is like an array of characters. So, these complicated things that don't make a lot of sense until you really study them are great places to find vulnerabilities, because probably most people are just as confused as you. So yeah, I consider that one of the big downfalls. You can't just do strings in C. So it's taking a character array, which is a string, which is going to be our argument. So input from the user is now in function 1. So the user has some control still. So there's a local variable, char, character, call it buffer, and it's 5 bytes long. Some of you may begin to see the problem. How many letters are there in Georgia? 8, right? 7 or 8. I should know this. Certainly more than 5. So we have character array. It's just a local variable. Remember, local variables go on the stack. So we are going to, in the next line, it does stir copy, and it takes its destination source, which is another silly thing. It's like, why not source then destination? But that's just how they do it in the C. So we're copying str, which is our user input, starts at argv1, so that's our user input. It's passed to function 1 as its argument, character string, and it is copied into buffer. And this is just a built-in C function. You don't see any code here for strcpy. This is a built-in C function, and it gets a bad rap. strcpy does exactly what it says it's going to do. It copies data from one place to another. It's not even a problem. It's like, if developers worked the way they should, it wouldn't be a problem. Because naturally you might be thinking, okay, I kind of gave it away, right? I'm like, my name is like 8 characters and there's only 5 available. What's going to happen then? Is there some sort of you don't see anything that's like a third argument that says only take the first 5 characters? No, strcpy is going to do exactly what you tell it to do. It's going to take every character of our str, which is kind of short for string, and copy it into buffer. If it doesn't fit, it's just going to keep copying. Some of you are probably having a light bulb now. Oh, very cool. So, but that's not to say, if you ever work in code review and you see strcpy, it's not automatically wrong. The developer could put in a bounds check of their own, make sure before they do the copy that things fit where they should. But there's also str in cpy, and that does have a third argument for how many. So with strcpy, you have to do your own bounds checking. If you don't want to do your own bounds checking, then there's functions available that'll bounds check for you. I don't know. They weren't thinking security when they wrote this. So then that's the end of the function. The function's over, so we're going to return to main. So all we've done is copied some stuff onto the stack. Not incredibly exciting, this program. And then it will, so function 1 will end, its stack frame will disappear, as we said. Well, it'll still be there, but ESP and EBP will return to main. So ESP at the top, EBP at the bottom, and then that return address that we saved on the stack will be loaded into EIP, and we'll pick up where we left off with main, and it says executed normally. So it will print out to the screen executed normally if things did indeed execute normally. But there is a third function. As it is, this third function is never called. You can think of it kind of like debugging code. I mean, this happens. People like leave debugging code in, and it is compiled, it is in memory somewhere, even if it's never called, it's there. If we can get execution to go there, it will execute. So that's actually going to be our goal for this first exercise, which I'm hoping to get 2 in, but I better get on with it. I want to show you a real program as well, not just one that I wrote, but we'll see how fast I can talk. So our goal for this first exercise is actually going to be to get that function overflowed to execute. Overflowed is even simpler than the other two. It says, all it does is print execution hijack to the screen. So that's our goal. Because if the program runs normally, overflowed is never called. So our goal is to make execution hijacked print out to the screen. So we know there's a vulnerability potentially here in function 1. This strcpy, we only have 5 characters allotted to us on our stack, but if we put more data in there, something might happen. Our goal is to turn that something into code execution. All right, I told you I do this. So stir copy does not do bounds checking. Then it will continue copying. Compiling a program, GCC, and you see this is another turning off things. I turned off the stack protector. That's a stack cookie. It's also called a stack canary. Again, it says we will discuss this later. But just basics of it. Stack canary is kind of to stop what we're doing. It basically just puts a magic number right above that return address that we saved on the stack. And then before it returns to main, it checks to make sure that magic number is right. So if we overflowed, we would kill the magic number as well. Again, bypassing stack cookies is another story for another day. But again, if you're doing this yourself and things seem weird, it's probably because it has the stack protector on. If it puts out that it says stack smashing detected, execution halted, it's probably the stack protector. So that's that. All right, running the program normally. So we just call overflow test. That's what I called it. The -o is just naming it. It'll call itself a.out if you don't name it, which is fine. So it will, if I give it 4 A's as my user input, so 4 bytes, each character is 1 byte, so we have 5 bytes. Putting 4 bytes in should be perfectly fine, and it should execute normally. Well, I should probably bring up the VM for this now. Something was bouncing. I hope it wasn't you guys. Go to webinar control panel. All right, cool. You don't see anything on here. All right, so I don't see any questions. I'm just going to continue. If I do see questions, I'll do my best to answer them. I'll give you my contact information at the end of class. If you have any questions that, or, questions about anything really, I will try to get to them all. I think there's a different place you guys are putting them that I'm not even in. Anyway, all right, moving on. All right, so I have the VMs. Again, they're old. It's not really matter. So again, you'll get the VMs at the end of class. I apologize for that. All right, so this is just my special little Ubuntu. And we are going to do something some of you guys may have not done before. We're going to play with the terminal. If you grew up on Windows before PowerShell, you probably hate the terminal because using the terminal before PowerShell and Windows was just pulling teeth. On our Linux-based systems, the terminal is a lot better. So if you're afraid of the terminal, get a Linux machine because honestly, you can do everything a lot better in the terminal in Linux. So let me make this a little big. Oh, right. We're not on a, I always make things really big because it's on the projector, but you guys actually see it on your screen. Never mind. All right. So again, the password is password, and you'll see we have overflow test.c on here, so you will have the code that we just looked at in the slide. Same code exactly is right here, except the formatting is better. So that code will be available to you, and I also have it already compiled as well, so that bit with the GCC you don't have to do it. So if we just run /, that means like run it from this directory. So yeah, and overflow test, and if we give it, like it said, like 4 A's. Why 4 A's instead of 5 A's? Oh, right, you guys can't talk to me. So actually strings in C are terminated with a null byte. So that's just 0, 0. That's how strings know that, or the computer knows that the string is done, is that it's null terminated. Certainly strings not being null terminated, you may have seen stuff like this, like you put in your name and then it puts out your name with like a bunch of junk after it, like question marks and stuff, unprintable characters. That's probably because the developer didn't null terminate the string. So that's awesome for memory leaks, but you know, another story for another day. You guys would, I'm sure, get tired of me if we did it that long. So I'm actually putting in 4 A's because we have 5 characters and the 5th one is a null byte. So you actually have even less space than you thought, because you need the last one for the null byte to terminate the string. So I'm actually just giving it 4 A's, and we expect to see executed normally. And that's exactly what we see. So far so good. The program actually does what I said it would do. That's a good start. So, you know, this one I'm just like, all right. So, you know, I haven't even made it a slideshow, but we'll be here for like 2 seconds. All right, so if we run overflow test and we just give it like a ton of A's, and these don't have to be A's. At some point, people just decided it was going to be A's, that we were going to do an exploit development. It could be B's, it could be C's. You know, as long as it's not like a special character, like you wouldn't want to put in a null byte, but you can't print that anyway. But you know, generally speaking, you're probably good in your like alphanumeric range. But you know, the first person that like did a write-up of exploit dev, I guess, way back in the day, used A's, and so we still do. So yeah, what's going to happen if we just give it a lot of A's? It's not going to print out executed normally. It's not going to print out execution hijacked. It's just going to crash. Crashing is, I mean, denial of service is valid, but code execution is better. So, you know, prove that I'm not lying. You know, and it doesn't matter really how many A's at this point, just like kill it. Segmentation fault, so it's like, I can't figure it out. So let's see what actually happened. So we're gonna use, we briefly saw GCC, that's GNU compiler. It comes with GDB, this is the GNU debugger. So again, if any of you guys are programmers, you may have used debuggers before. Debuggers are awesome for debugging your stuff, but they're also really awesome for exploit developers or otherwise, you know, people in the hacking business, because you can see what's going on in like memory and things like that. So basically what happened, just make it big. Play from current slide. All right, so when strcpy runs out of room in our buffer variable, which it invariably will because we sent it tons of stuff and it only has 5 spaces, it will just keep copying data into the adjacent memory addresses. So it'll overwrite any additional space in our stack frame for function, and then it will continue writing. Like it will write literally to the end of the stack if you give it enough information. strcpy will just do it. Again, not necessarily a bad function. If you're into writing bounds checking yourself, it can work perfectly fine. But as it is right here, it's not good. So it's going to, if we give it enough data, just keep overwriting everything on the stack. What's the interesting thing we put on the stack that we said we wanted to control? That saved return pointer for main. So if we, basically what I'm alleging here at least is that if we give it enough data, we can overwrite that saved return pointer. I mean, at this point, we're just giving it junk and it's not going to be able to figure out what to do, but, you know, we can give it other stuff. No? All right. Oh, this one looks right. Ha. So here's kind of a picture of what would be going on. So there's a variable buffer that is a local variable, so it's in function one stack frame, and you know we put some A's in it. You know there's 5 spaces, and then it keeps writing A's. It writes A's because it's 32-bit. The addresses are 4 bytes, so everything is 4 bytes. A. And then it will even, like I said, it will write it into main. It will write to the very end. If you keep doing this, you may see issues where you actually will write to the bottom of the stack frame, and that's what causes the exception. So, you know, check your bounds is the overarching, I guess, thing if you don't want this to happen to you. So attaching to GDB, you really just say GDB and overflow test. Tell it we want to use GDB and debug our overflow test program. Do not use overflow test.c because that is just code. We want it to actually run the program. And, well, let's do it. All right. I don't know why I thought it was such. GDB overflow test. My typing is terrible. I apologize. Overflow test. All right. So we get some, like, you know, this is the license and all that stuff, but then we get a GDB prompt. So we currently have the debugger hooked up to overflow test. So I said the debugger was cool, and indeed it is. Probably the first thing that anybody needs to know about it, though, I need like 2 monitors and just switch back and forth. So breakpoints. There are a lot of things you can do in the debugger, but like I said, probably the most important thing to know, like starting out, is breakpoints. So what breakpoints do is they stop execution at a certain point. So you give it a memory address, name of the function, anything like that, and it will stop. If we're running the program and it hits that breakpoint, it'll just pause, completely freeze. Memory will stay the way it is. The registers will stay the way they are. Everything will just be stuck in that configuration until we tell it to continue past the breakpoint. That's really interesting for us because we kind of want to see if I'm even telling the truth at this point, that it actually does what I say it's going to do. But as you move on, you can certainly imagine that you might use it as well. So it allows us to examine the state of our memory, our registers, everything at that certain point. So that particularly should be cool. So because we actually have the source code, because it's on the same machine and it's just like sitting there, and it's you won't always have the source code, but again, we are walking before we're running, so you can actually list out the source code in GDB. So you just, again, I don't know where these people come up with this as a syntax we're going to use, but it's list, and then you tell it where you want to start and where you want to end. So you want to print out lines 1 to 16, in this case, the entire program, and it will print that out to the screen. Again, this will not always be available to you. So we can tell it to break at a line number. You can also tell it, again, at a memory address. You can break it. You know, look at the GDB man pages if you want to see like all the things it can do. So we can tell it a line number that we want to break at, since we have these. So if we wanted to break like right before the strcpy, I'm saying like this is our problem function. strcpy, probably seeing like what's going on before and after it is probably a good place to start. So we might want to tell it we want to break at line 10 and line 11 right before strcpy. So if we break on 10, it will stop before strcpy is called. And then if we break at 11, right before it returns, then strcpy will have happened. And since that's supposed to be the problem, we should see scary stuff happen. So you just have to say break. I also have us breaking at line 14. If you look at what line 14 is, it's right before the function call. So that's just going to have us in main stack frame, just for, our information. So again, you just say break and then the line number that you want. I have us breaking in main right before the call to the function, and I have us breaking right before and right after our vulnerable function, that strcpy or stir copy, however you want to say it. So we can do that. So break 14. Well, first let's actually do it. I hope you guys aren't hearing that awful noise. All right, so there's our source code, and we want to break at right before the call to function, so we want to break at 14. Breakpoint is set, and it has a memory address for it. Then we want to break at 10 and at 11, so right before and right after the stir copy. 19, really? Break 11. All right, so we've got 3 breakpoints, and they should all be hit because we end up there. If we set a breakpoint and overflowed, it would never get hit, so it wouldn't matter. But so we should expect our program to stop 3 times in normal execution. I try. Oh, I went up, not down. All right, running the program in GDB, you just have to say run to run it and then give it any arguments. So again, we can just start with 4 A's. Remember, the 5th byte is that null byte. Null terminators are important. Memory leaks are a big deal. So definitely always null terminate your strings so it doesn't just print out things from memory. Not that. I try not to put up any crap in class, but it doesn't always work out. Actually, that was a PDF copy of my book anyway. All right, so we want to run, again, it doesn't have to be A's. To run with 4 A's, it hits the first breakpoint. So that is our first breakpoint. It's going to be in main because it's right before the call to function. So here we are at line 14. So we are broken in main. Function doesn't even exist yet. But go down here and you can view your registers. Remember the registers: EIP, ESP, EVP, EAX, ESI, all those other ones. You even see more stuff than that. Don't worry about the segments for now. These are just the data segment and stuff like that. But we want our registers. So you can view your registers just like with info registers. Additionally, you can view memory. There are a lot of ways to view memory. This is another one where it's a whole chapter in the book on GDB, I imagine. But you can view memory. The example here is X is examine. So we want to examine 20 hex words. So 24 byte things from ESP. Remember, ESP is the top of our stack. And then we can, down here, it's examine. Well, 1 is the default 1 hex word from EVP. EVP is the bottom of our stack. It may not actually come out the same as on the slide in terms of the memory addresses because it might move around, but let's see. Let's actually do it. All right, so we are stuck here at main. We can do info registers, and we see ESP top of our stack, EVP bottom of our stack. I mean, you can see it now. I realize these are in hex, but BF, E5, 1B, those are the same, but the last byte 98 and 90. So EVP 98 is higher than 90. So as I said, ESP is going to be at the lower memory address because the stack grows up to lower memory. So that kind of makes sense. It is actually doing what I say. So again, X for examine, slash, and then 20 is probably too much, but 20 hex words from, oh God, don't kill the computer, from ESP. So that's going to start at ESP, which we saw was at BF E5 1B90. Sure enough, it is. So this left-hand set with the semicolons, that's the memory addresses. So yeah, so hexes base 16. I can hardly count base 10, so bear with me. All right, so this is going to be the top of our stack, and then it said, so we can do it here. So if we examine just one hex word from EBP, the last byte is 98, which in our registers, that's what it says it should be. That's not entirely surprising. All right, so it's the data in there, which data can just be junk or it can be useful. BFE5 1C08, right here. So this highlighted bit is actually main, wait, that's not right. Top. The highlighted bit here, that's actually main stack frame. It's quite small, but main doesn't really do anything. It just calls another function and then prints out stuff to the screen. So actually, it's not entirely surprising that it's small because it's just for scratch space. But it all does what it says it's gonna do. We have a little place for it, but things are gonna start to get more interesting when we actually keep going. So to pass a breakpoint, you just say continue, and then it will run until it hits the next breakpoint. Remember, the next breakpoint is at line 10, right before the call to strcpy. So we should expect, we are now in function stack frame, and we should expect to see the return address of main pushed onto the stack. And again, that's what we want. But we shouldn't see any A's. Well, there may be some, but we should not see like 4 A's next to each other in memory yet, because the strcpy hasn't happened. Well, in function stack frame anyway. So then you can hit the up arrow, which I love because I'm not the best typer ever. So before main stack frame was here, right? Its last byte was 90. So this was main stack frame. But now ESP is up here where the last byte is 70. So, and then we can do EBP as well. And so that's at last byte is 88. So that would be function stack frame at the top. We don't see any A's at all. But more on that later. And then so that's function stack frame, and this is main stack frame. Anybody have any ideas what this 4 bytes here between the two? Remember, this is function stack frame, main stack frame, 4 bytes in between. So if we go back and look at our pictures, you can probably figure out what it is. So if we go a few back here, like for this one, this is after overflowing it, but you see you got function stack frame, main stack frame, and right between the two you have the return address. Addresses are 4 bytes in 32-bit, so it makes sense that it's 4 bytes. It's a memory address. It's probably the memory address of the next instruction to be executed in main, based on what I've said, assuming we believe anything I say. This is all just, it's just, again, exactly what we're doing. I'm trying to use more slides, but again, you'll get it all. So anyway, so this is, or should be, the return address of main. Now, we can either believe it, or probably better, since we're just learning, we can verify that. So I said you didn't have to know any disassembly, and I meant it. But you can disassemble in GDB and look at the assembly code. So even if you don't have the source code, you can always get the assembly code. And I know assembly is kind of scary at the beginning, but in general, it's we have Google. So, honestly, if I forget something, I'm just like, what does this mean? And Google tells me. So, okay, so disassemble main. And yeah, it looks like assembly instructions. But we see a couple we already know, like we know push, that pushes something onto the stack. MOV, that's move, so move one thing to another. Add, pop, sub. I mean, most of this doesn't actually look that scary. But anyway, I said you didn't have to know it, and you don't, because it's really obvious to see where we are, because there's a call to function, and obviously that was the last instruction that was executed in main. It called function, so we should expect the return address to be the next address, so it should be 08048443. And if we look back here, remember this was function one, or is it function or function one? The function stack frame is here. Main stack frame is here. So this, we said, is the return address of main, 08048443. It's exactly what we would expect it to be, the next thing to be executed in main. How awesome that a computer actually does what its man pages say it will. So cool. Now let's do our next breakpoint. Remember, this will be right after our STR CPY. So we only gave it 4 A's, so we don't expect it to crash here. Everything should be fine, but we should expect to see our 4 A's being copied into our memory. So we continue, hit our third breakpoint. We should expect to see some A's. Anybody see any A's? Look kind of weird, doesn't it? Well, you won't actually see an A because you actually are looking at it, you're thinking ASCII, not hex. So the hexadecimal representation of an uppercase A is a 41. So it's, you can look at like ASCIItable.com that has like the complete set of what's what. Big A is 41, big B is 42, big C is 43. But again, you can always look it up. I like my Googles. So what we actually see here is, it looks kind of weird, and we're going to see why it looks weird, but I said big A is 41. If we look at it before we continued, so up here we have what things were, and now we have what things are after the string copy, and we can compare them, but we said it's 41, so here's 141 here, like at the first byte of this one, which seems kind of strange. And then with this one, it's the last 3 bytes, and then we have 00, which that's our null byte that we talked about, terminating the string. So it looks like we did get our 4 A's and then the terminating null like we expected, but they don't look like what we would probably expect them to. Like, why is this over here? Like, if it's gonna be over here because it's 5 bytes instead of 4 with the null byte, like, why isn't it at the end? And why is the null at the beginning? This is so confusing, you computer science people. Why did you do this? All right, some of you may know, I always harp on this because when I was starting out in exploit development, I guess I was sleeping that day in computer science class because I did not remember this at all. And it took a lot of time for me to figure out why everything was backwards. But we'll talk about that in just a second. If we do continue, we see that the return address is the same as it was before. The next instruction to be executed in main, and that's, we only gave it 4 A's. We used the program as it should be used, so they do get copied into memory, but they don't get far enough to hit this guy. So that makes sense, right? If I can spell continue. All right, so if we continue, it says executed normally, and then the program exits. Everything happens as it should. So the first question I want to answer is, what happens if we give it a ton of input? And then the second question I want to answer is, why is everything backwards? And then the third question would be, how do we turn this into like a working exploit. Remember, our goal is to make it print out execution hijack to the screen. So some of you might be thinking, well, we need to get the address of execution hijacked here. You're absolutely right. But how do we do that? So first, I want to run. Remember, run is how we run things. And just, again, give it a bunch of input. It's just as long as it's like a lot. It's not even that much. And then see what happens. All right, our breakpoints are still going to be set. You can delete breakpoints with delete if you don't want them anymore, but you know, they're all good for us. So we run, hit our first breakpoint. Again, nothing interesting really happens in main, but one thing to take into account, remember on our last one, the last byte was 90. It's not anymore. It's actually moved in memory where the stack is. You know, I said we turned off address space layout randomization. So you might be saying, like, why is it moving in memory? Well, where the stack goes has a lot of like inputs to where it goes. One of them is actually the length of the function. So when you're changing how long your input is, it will move the stack. The location of the stack does not matter. It's just scratch space. You know what we were interested. This is a memory address for the saved return address, and if we go up, you know that we don't want to move. That's what we were stopping with ASLR. The program, the code for the program, and the code for the built-in functions, they will not move with address space layout randomization turned off. If it was on, they would move, and we wouldn't be able to hard code addresses. And you know, if you continue your studies, you will learn much about that. But where the stack is doesn't matter. We're not returning to the stack. The stack's, you can really just think of the stack as junk mostly. So it's not a problem that it moved. So, all right, let's continue. We hit our second breakpoint, and you know, again, this is right before string copy, so you know, everything should be. But notice what hasn't changed. You know, I didn't say this up here, but like EBP and ESP, so despite the fact that it moved, so this address over here on the left, it moved. It's different. But the size of the stack, remember it was just, you know, 3 sets of 4 bytes? It's the same. As we see, our EBP is at 08 and it's, you know, 78 here. So the size of the stack frame doesn't change, just where it is does. That will come into play. All right, so now we're in function, and again, it is the same size as well. It's obviously not in the same place either, because it's just put right on top of main. And this is where our address space layout randomization being off would come into play, is that you see this address, if you look back up, that's the same address in main 08048443. And so our return address is the same. And our size of our frames are the same. So the only thing that's changed is where it is in memory. All good. All right. So this is where things should get interesting. So if I continue and let that string copy happen, remember we gave it, I guess I gave it 37 A's. I didn't really count, but I gave it a lot of A's. And remember they like last time they were like here and here. They're gonna like copy down the stack. So theoretically we're gonna overwrite this and it's gonna be all 41s. Continue. Here we are at our third breakpoint, and if we again examine memory, indeed, it looks exactly how I just said. So we have, you know, our 141 over here all by its lonesome. We'll talk about that directly. You know, we have our 41s, and it just keeps copying. strcpy would just keep copying. So really what the problem is that the stack grows up, but it writes down, or the other way. It grows to lower memory, but it writes to higher memory. So it's not just going to write into like future stack frame junks that isn't allocated yet. It's going to write into stuff that's already on the stack, and this can be disastrous, as we'll see. So again, I would love to be in the room when someone decided things should be upside down and grow towards each other, but I wasn't, so that's that. So I can just take for a fact that that's what happens. So remember we saw 08048443 as our return address in main. We, in our last run, disassembled main and saw that was the next instruction to be executed. But now that we've done our stir copy, we see that that has been overwritten by 41s. So 41, 41, 41, 41, I mean, it's all hex. It could be, I mean, it could be a real memory address, but there's probably not anything there. And you'll also see, like I said, it'll just keep writing. Like this, it's corrupting main stack frame now. Like it's just, and then again, the null bytes over here at the end. This doesn't make any sense. What's going on? Everything is backwards. So, if we let it continue, what we should expect is it's going to try to execute whatever is at memory address 41, 41, 41, 41. There is nothing that says that you can't put things there. You may have programs that do have 41, 41, 41, 41 mapped to an actual piece of code, and it would execute somewhere randomly. But as we'll see in this case, and most cases actually, it just gets confused. It's like, I don't know what 41, 41, 41, 41 is. It's not in a function. I'm freaking out and I'm just gonna die and give up. So yeah, the program just stops. So, I mean, if this was like a web server and we were a bad hacker and we didn't like them, this might be good. We brought it down. They're not making any money right now. If they were like Amazon, they'd be losing like tons of revenue in like the few minutes it takes to get it back up, I'm sure. So, I mean, denial of service has its uses, definitely. But again, we want code execution. We want to take this a little bit farther. So just like writing A's into it and making it crash is not good enough for us today. So our goal is going to be to get something interesting there that's not going to make it crash. You might guess since we want it to print out execution hijacked, and we have a nice function that does that called overflowed that currently never gets called. Remember, if we look at our code, we have that top function overflow that just prints out execution hijacked. If you recall, our goal is to make it call that function and print execution hijacked to the screen. So you might imagine that we would like to get the memory address of overflowed in the place of those 41s, and you would be absolutely right. But the first question that we have to solve is, what happens if we overflow it? It's seg faults. It's bad. We killed the memory address of the return address, which is bad because it made it fall, but it's good because now we can exploit it. That's awesome. But I still want to answer this question about, we've got this one over here. The null byte is like right, where's the null byte? Right here, like by itself at the end. It doesn't seem to make any sense. So again, I want to harp on this because it was difficult for me, and if you already know this, my apologies, but I like to make it so people don't make the same mistakes I did. All right, so I want to run it, and I'm going to run it this time. All our A's are all 41s, right? So I want to actually do A, B, C, D, because A will be a 41, B will be a 42, C will be a 43, D will be a 44. Again, ASCIItable.com. There's actually even a man page. I think it's man ASCII. Let me new tab, man ASCII. Yeah. So yeah, you have the internet, but it's also actually, if you're not familiar with man pages, man is short for manual, and built into your Linux systems, you have manual pages, so you can Google things, but you can also, in a lot of cases, if you're like at a government thing and don't have any internet, they actually have manuals built in for a lot of the built-in stuff. So we think in the chars, right? We think A, B, C, D, what have you. But the computer thinks in hex, which is base 16. So, it's 1 to 9, and then A, B, C, D, E, F, and that comes out to be 16. Well, there's also the 0. Yeah. So, again, if you took computer science at all, they probably made you learn this. I don't remember it at all, so I use this. But you can also see there's octal and decimal and hex and what the actual chart is. So, big A hex representation is 41, big B 42, C 43, D 44. Excuse me. Post COVID, coughing is like, I'm always afraid people are going to kick me out of like my barn or something. I never go anywhere, but I have terrible allergies. Just a side note. But I guess you guys aren't in the room with me, so you don't care. All right. So we can quit the manual page with Q. That was, again, just a side note to prove that I'm not lying. So let's run it with ABCD and see what happens. See if it can help us get to the bottom of why is everything weird and backwards. Oh, well. It still thinks it's running because it crashed, like it didn't finish. So do you want to start it from the beginning? You just say yes. That's just how it works. We could look at our memory of main. Again, it's moved, but let's continue and go. I actually want to look at our third breakpoint because we've already done it with 4 characters. We did A, and we saw what happened. We want to see it with ABCD. So I'll just go to the third breakpoint, and now I want to examine memory. All right, so we see things are as they should be. So again, same size. The size is not going to change, which is going to be important. And then here's main here. Here's our return address, 08048443. And that's, again, not changed. That's the memory address of the next instruction in main. Because we only gave it 4 characters this time. It did not get corrupted like last time. Last time, remember, that turned into all 41s, or the representation in hex of the big A, because we overflowed the boundaries of buffer and ended up overwriting the stack. All right, but in this case, we did not. We just gave it ABCD. All right, so now we can kind of make more understanding about what was going on. All right, so we only gave it 1A this time. So this is the first character that we gave it. So it's over here, and it's the first byte, which you would think it would be the last, but it's the first byte. And then the B is the last byte of the next one, and then there's the C, and then there's the D, and then there's the null. What on earth is going on? Everything is backwards. All right, so yeah, everything we've just done, we'll just go through it all. All right, here's what we want to talk about. All right, Indianness. So, it's not like people from India. It's you see, it's spelled with END. So it's literally which end do you load first? So you can load like the first byte first or the last byte first. I have if you just look up Indianness in Google, I have one link down here at the bottom to more information. This is, again, one of those things that the powers that be decided how things were going to be. So just a little side note of trivia. This is always the trivia question that I ask. So all of you, if you're ever like winning a door prize and I have to do the question, you'll know the answer. So where this Indianness came from is actually, it's from Gulliver's Travels, the book. Well, you imagine Gulliver travels in Gulliver's Travels, and indeed he does. And one of the places he goes to is called Lilliput, and they are in a war with these other people, and the war is about which side of the egg you should crack. Like the little Indian people think you should crack the little end of the egg, and the big Indian people think you should crack the big end, which, I don't know. That seems like a really silly reason to be fighting, but computer science people do it too. So there are big Indian architectures. Big Indian architecture, we wouldn't be having this discussion because everything would just look normal. But a lot of processors are little Indian, which is what our Intel is. So that's why everything is backwards, is because it's taking the least significant byte first, and the most. So basically everything's backwards. Again, here's a link. There's tons of like theory about it, and But all you need to remember as an exploit developer, when I'm doing little Indian, I need to flip my bytes around. And that seems to be what's happening here. That seems like a pretty good explanation of what's going on. So we have our 41 by itself over here, and it's at the, what seems to be the first byte. But if everything is backwards, so if this is the beginning, we're loading the least significant byte first, then the 41 would become the end, the last thing loaded, and that would make sense. And then again, so we start here with 42, load the 43, load the 44, load the null byte. So again, there's a lot of theory. We could be here for a long time about it, but as an exploit developer, lots of things are little Indian. You have to flip little Indian backwards, and we're not doing it character by character, right? It's not like 1 and then 4. We're doing it by byte. So it takes 2 hex digits to make a byte. So this is 4 bytes, 8 hex characters. So F4 is a byte, EF is a byte, B0B is a byte, 41 is a byte. So that's not 14. We haven't taken our big A and turned it into 14. It's still 41. So we're flipping it around byte by byte, not character by character. Again, I don't know why they can't just talk base 10 like everybody else, but computers will do what they will do. So in that case, it kind of makes sense. Again, it's probably like, but why? And, Google it or look at that link or, remember your computer science classes better than I do. So that's why everything's backwards. It's just an architecture thing. But again, if you remember your Gulliver's Travel trivia, that's always what I use as a giveaway. So if you ever see any of my talks and they're doing giveaways, come get your book or whatever. All right, so our next goal should be, so we said we had 3 goals. We wanted to see what happened if we overflowed it. We crashed it. We denial of serviced it. We turned our 080484443 into 41, 41, 41, 41. So we can get control of that return address. Awesome. Our next question was, why is everything backwards? And we at least a little bit explained it, right? Because they say so. Just turn everything backwards. So that's good. So our third thing that we wanted to solve was actually turning that into, instead of a crash, a execution hijacked being printed out to the screen with that overflowed function. So maybe we can do that. I mean, in a lot of cases, and everything's really small here. This is a really simple program. So, probably in most cases, you're not going to be able to count. But in this case, you could. I mean, it's like, all right, so we gave it 4 bytes, right? So it's like 1, 2, 3, 4, the null byte. So 5, 6, 7, 8, 9. And then the return address. So it looks like we just need like 9 bytes of padding. So, right, we're starting here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then our return address. So remember, our stack frame sizes are not changing. Where they are in memory, this left hand, yeah, that's going all over the place. But the actual size of it is not. So no matter how many times we run it, we're still going to have our first character here, 2, 3, 4, 5, 6, 7, 8, 9. So it should just be always, no matter how many times we run this, there should be 9 bytes of space in this function stack frame before we run out to the end of the stack frame and hit this return address. So to prove this, as we will, I'm going to run this again. Well, let me finish it. See, this time it executed normally because, again, we only gave it 4 bytes. We used it normally. So I'm going to try it again, and I want to actually give it 9 A's and then 4 B's. You can do this. You can also script inside of, like this is an example. You can script inside of GDB. So again, because this is small, we could just write, a 9 times. Wait, that's not, where did it go? Oh, down here at the bottom. So ignore the slide except for the fact that, well, not really, we're actually about to do it. So we say run, and then you put the $, and then you can actually script inside of it. So clearly I was still in my Perl days when I did this. I used to write a lot of Perl. Now I write Python. Python is awesome. But you can script as long as the Linux system knows the programming language, which most of them come built in. And if your language of choice doesn't, you can just install it. You can actually script inside of it. And then, yeah, but you can also not if you want to. But yeah, this, it just says Perl execute print a, in this case, times 17, and it's an X. This is why I don't like Perl, because it's an X, and then instead of a plus, it's a dot, and so it depends on your programming language. But again, this time it's so small, it doesn't matter. All right. So, we could do run, and let's do it in Python. So $, open parentheses, and Python, -C, like -E is Perl, -C I'm pretty sure is Python. Do I have to put parentheses around that? No. Single quotes. Google is your friend. I half joke that I wrote my book so I could look at my own book to look up things that I forgot. Again, half joking. So we want to print a times, because in Python, times is actually a time symbol. A times 9 plus, again, this is all, it's programming language specific. If you don't want to do programming languages, you don't have to. But it comes in handy. And then plus B, and I'm going to do times 4 times 4. And remember, that's because 32-bit architecture, 4 bytes. So, we've got 8 characters, which is 4 bytes, because it's 2 bytes of, or 2 characters of hex to make a byte. Now I'm confusing myself. But anyway. So what should happen in this case, assuming I've gotten my syntax right, which is totally possible I haven't, is we should expect to see our 9A's, so 941s, filling up here, and then our lonesome one over here. But remember B, uppercase B, we looked at that ASCII table. Actually, I still have it. No, I don't have it open over here. 42 is big B. So what we should suspect to see is our 08048443. That should actually turn into 42, 42, 42, 42. That will allow us to pinpoint the exact offset of our return address. As you become more comfortable with exploit development, you might skip this step. You might just, believe it was right. But, one, we're learning, and two, I've always found that skipping steps generally leads to something going wrong later. But again, it's up to you. All right. Hopefully my syntax was correct. All right, we've still got our same breakpoints. Again, you can delete them. Main's not very interesting. It's just there. And we can continue to our second breakpoint. And, things look normal. We're in function. Same old story. This is function, stack frame. This is our return address. Yet again, 08048443. That is not changing every time we run the program. That's where it needs to go next. And then, we have main stack frame here. So we've not done the strcpy yet, but we are about to. And so if we continue to our third breakpoint, again, what we are expecting to see is our lone 41 here. These are all 41s, big A's. These will be all 41s, and we should expect, we only gave it 4 42s or big B. What we want to see is all those 42s, all 4 of them right there. If there's a 42 that dropped off and one of these is a 41, we know our offset is wrong and we need to adjust. This might seem kind of silly, but it's not always going to be 9. You'll look at ones where you have to do like A times 1,100, and in that case, you can't really like count the A's. So, in this case, it's real simple. It's a good way to start, but these things get bigger, and you won't just be able to look at memory and count. I mean, I don't think I could anyway. So, just take that into account. All right, let's continue and again see if I'm telling the truth. All right, we hit breakpoint 3, which is right after our call to strcpy. If we examine, all right, things are looking good. So we see we've got our 141 over here. That's our first A. We've got some more here and some more here. So our 9 A's seem to have done exactly what I was hoping. And then remember, see, it's the second line on the right where it's always been. That was our return address. Now our return address, 42, 42, 42, 42. So that looks good, right? Again, we only gave it 4 B's. If those B's are there, then our offset is right. So that looks perfect. Perfect. All right, so now we have what we need there. But again, if we just let it continue, we get the same result as we did with the A's. That's not mapped, it's not mapped in memory, so there's not any code there for it to run. So it gets confused and it gives up. So we need to change that into something more useful. So remember we disassembled main, haha. Remember we did this when we were trying to see, was that the return address? And we saw, here's our call to function. And the next instruction after that, it's memory address. Remember our saved return address, that's our memory address. It's not actually going to be like movel, whatever. It's going to be the memory address. And we saw that over and over again. You can probably say it with your eyes closed now, right? 080484443. Did I get it right? Yeah. Okay. Because again, that's not changing. So, that's our memory address that it should go to, but we want to send it somewhere else. And, as you do more with this, you might, unfortunately, I've never done 2-hour class before. Like the next exercise, you actually like put shellcode. If you've not heard of shellcode, it's basically adding your own code into memory, and then you send execution to the beginning of your shellcode and make it execute. So it might open up a shell and call back to your attacker machine. It might open calculator. It might, do whatever it wants. But in this case, and certainly data execution prevention, which we didn't really talk about at all. It's another anti-exploitation technique. It says people should not be executing off the stack. So we should not be able to just put our own stuff, like our own shellcode, instead of A's, like we would put like a ton of characters that were hex characters to actually execute code. You should not be executing off the stack. The stack is scratch based, so it should not be executable. So data execution prevention makes the stack non-executable, and makes, just putting shellcode on our stack and executing it not work anymore. How do I want to say? So things like this where we can find other code. I mean, in this case, again, it just prints out execution hijacked. It's not that serious. But I mean, you might be able to find code or pieces of code that you can put together to make it do what you want, which is a silly explanation. But basically what I'm saying is that while this example is easy and contrived, it's not really that contrived, because it just could be something that you do especially with our most modern platforms, like with the iPhone, where everything has to be like signed. It's being able to look through memory and find code that you want that is executable, because this is all like code that it's executable. Obviously it's being executed, is definitely a good thing. So yes, I just put we'll say a debugging function that does what we want. I didn't take it out. I didn't comment it out, if you're not familiar with comments. So you should comment your code on like me. Different programming languages have different symbols for it, but if I commented the code out, it would just become like extra information and it would not be, compiled as code and sitting in memory. But because, I left that in there, it does compile and it is in memory. So overflowed exists. So we'll say it's like debugging code. Say it's like a backdoor that they left in there, and it happens, believe me. So that's that. All right, so that's our goal. We want overflow to run. So just like we disassembled main, right? Why don't we disassemble overflowed and see what happens? All right, so here's overflowed. So if I want to send execution to overflowed, my guess would be the best thing to do would be to send execution to the beginning of overflowed and let it run. So instead of, sending it 42 and crashing it as we did, we crashed it with our 42s. If we send it a valid memory address, so this is where the code is, so it's valid, it's executable, it's for real, then we should, instead of just crashing it, make execution go where we want it to. So we're kind of, well, running out of time too, so this should work out well. All right, so again, I love the up arrow. Love. All right, so I go up to my original run. Again, I did mine in Python. The slides are in Perl. I'm pretty sure the book's in Perl too. I was deluded. Python is much better. So instead of our b times 4, this is why I mentioned being able to do it with scripting, because sure, we could have did a 9 times and b times 4. I mean, one of the reasons is you're not going to print out a 1,100 times. But in addition to that, this is a memory address. So, if I type in 080483F4, it'll see each of those as a character, and we want it to see it as hex. So, most of them are probably unprintable anyway. So, our goal would probably be to use a programming language at that point. So I'm going to take out my b times 4 because I don't want to go to 42, 42, 42, 42 anymore. I want to go to 080483F4. And again, the syntax may change based on your programming language. So if you're using a different one when you play with this later, it might be a little different. But for me, on my Python, I'm going to open my string and it's \x, and that tells it it's a hex byte. So I'm going to go 08, because remember, 2 digits for a hex byte. So 08, \x04, \x83. And if you see what I did wrong, you're smart. And then F4, and then close my string. I always forget to close my string. So I have my string closed and I have my single quotes closed as well. So this should tell it, instead of 4 Bs, to put our 4 hex bytes there, 080483F4. So if everything goes as planned, then this should, instead of crashing or printing out executed normally, it should print out execution hijacked. So let's see what happens. Again, because it crashed, do you want to start at the beginning? Yes, I do. And then let's just continue through main. I guess I hit continue twice. All right, now let's look at, all right, so, as per usual, memory addresses, God knows what, but this is our stack frame for function. This is our return address, and this is our stack frame for main. All right, so our A's are still looking good where they were. A's. All right. And then we have, okay, we have F4830408. Does that matter? Is that how it's supposed to be? Is this an Indianness thing? Like, it's backwards, and it's backwards by byte, right? It's like, it's still 08. It's not 80, but 08 is at the far side, and then F4 is at what would be the beginning. So that may be a problem. Let's see if it's a problem or not. I mean, everything looks backwards, so maybe it's fine. Oh dear, we did not get execution hijacked printed to the screen because it tried to execute F4830408. So remember how I said in Little Indian you just have to flip everything backwards byte by byte? Literally, you can just like mindlessly, knowing nothing about Indianness whatsoever, you can just remember that if I'm Little Indian, I need to flip things around byte by byte. Or if I see something like this where things come out backwards byte by byte, oh, it's an Indianness issue, flip it around. Again, definitely if you're interested, like look up the theory, it's interesting, but as an exploit developer, all you got to remember is flip it around byte by byte. So theoretically, that should be our last problem. And since we have 8 minutes, then that's probably a good thing. All right. So let's go back to our run script. And this time I want to flip it around byte by byte, not character by character. I don't want it to become like 4F, 3.8, etc. I just want F4 to be first. 8.3 0408. So all I did was flip it around byte by byte. So if I put it in backwards, it'll come out forwards. Again, I don't know why they do that. And again, this isn't going to be universal. You may, like MIPS systems, they're probably not all big Indian, but a lot of them are. There are like things that are big Indian. There are things that are little Indian. So don't universally assume everything is backwards, but probably will be for a lot of things. It's just something to keep in mind too, like when things aren't working and they're backwards. Oh, Indianness. Yeah. Again, I had a lot of trouble with that starting out because I didn't know what it was. And people laughed at me, but they won't laugh at you. All right, so again, I'll just continue through the first 2 breakpoints. I think we've got it by this point. And then examine our memory. All right. This looks good. All right, we got our first 41. Our 41's here. These are our A's. See, everything's still good. And now 080483F4. Just to recall, we disassemble overflowed. 080483F4. So if it does indeed what it says it's supposed to do, instead of going back to main as it is supposed to and saying executed normally, and instead of crashing and saying segmentation fault, it should jump over here at the beginning of overflowed and execute it. You don't have to know assembly. I mean, it's pretty simple. It's puts outputs to the screen, so it's setting up his thing, it's calling puts, and then it's returning. It's real simple. So you disbelieve me on that one because we have the source code. So moment of truth. I think I have solved all the problems. Continue. Execution hijack. Code execution. You will see that it did crash afterwards. That's not always going to be the case, but in a lot of cases it will be. Like your shell will be running, but when you exit your shell, the thing will die. I mean, there are ways to clean that up and get things working, but certainly we can't do it in 5 minutes, and certainly it's not even worth doing at this point. So our goal we reached. We did execution hijacked, right? Does this thing have a notepad on it or something? All right, text editor. All right, so what did we do? I want to make it bigger if I can, but apparently I can't. All right, so it's little. All right, so what we did was ran the program normally. Ran the program abnormally. I can't spell normal. And I mean, again, fuzzing is just sending it a lot of input, but you can do reverse engineering if you're into the assembly, like, pop it into like IDA Pro Free Edition or anything like that, disassembler, and look for, vulnerabilities, look for, bounds not being checked, things like that. But you can also like think about it, like for instance, I didn't know this until I started doing exploit development, but did you know that like the length in Windows, the highest length of file names is 255? I didn't know that. So like if it's a file server, like if it's FTP or TFTP or anything that deals with files, like knowing that it can only be 255 bytes according to the operating system, but probably most programmers don't even know that. And if they're not checking their bounds, then the operating system is going to say it can only be this big. And what if I send it like 1,100 bytes? So yeah, there's fuzzing where you just can send it a bunch of crap and see what happens. You can do reverse engineering and find what you believe to be vulnerabilities in the assembly, or the third thing to do is like think about like what it's doing and where there might be problems. If you've run into similar things that have had like a problem, you might want to check like other ones for it, if that makes any sense. So we ran the program abnormally. We had the source code. In our case, we had the source code, which makes it even easier. We don't have to do assembly. We just have to look through it and be like, oh, strcpy doesn't check bounds. Oh, let's see what happens. So that gave us our idea to run the program abnormally. We did check our offsets. That was the A's and the B's. Check the offsets. Again, you can skip this once you're confident. When we send it like the A times 9 plus B times 4. All we did in that case was verify that our offsets were right. Again, this is really small, A times 9 and B times 4. I do want to show you one thing for that before we stop. So this we didn't get to Metasploit, but see, this is Kali, but any Metasploit, so in user share Metasploit dash framework, yours might be in a different place if you're not using Kali, but this is like the code and stuff for this. So if you go into, I think it's in scripts, might be in tools, I might be crazy. Yeah, it's not in scripts. It's in tools. So it's a Metasploit tool. Pattern create. You'll see everything has .rb. Metasploit is written in Ruby for whatever reason. It should have been Python, but nobody asked my opinion. So what you can do, because again, this is A times 9, so we could just count. You remember we did it. We counted how far away our return address was. When it's like 1,100, that's not going to work, obviously. So you could do pattern create and like 1,100. .rb. Ha! You actually have to give it the whole name. And then it will create this pattern. I mean, this isn't like the only way to do it. I mean, I'm sure in like the early days of exploitation, it would be like 550 A's and then 550 B's, and then you would just keep like cutting it. But this is a unique pattern. It's cyclic, so you'd be able to tell like, based on what came out, and then you can use pattern offset, which you also see, and then give it the 4 bytes that show up in your return address when it crashes, and it'll tell you the offset. So that'll allow you to figure these out when they're longer. Again, I have all the write-ups and everything for the next exercise that uses that. And then, we checked the offsets, found where we wanted to go, overflowed function in our case, and then we took Indianness into account and turned our overflowed address around backwards, and then it worked, right? And then it said execution hijacked. Really? That's a joke. It's funny. Don't like read too much into it. I thought it is closed. I closed the messages, stupid Mac. All right, I just ruined the video at the very end. But well, whatever. Okay, so I said I would give you contact information. Sorry, it's so small. Can't even think of my own email now. Georgia@bulbsecurity.com is email. If I don't write you back, email me again. I'm trying to do inbox zero now. Sometimes I just don't. I mean, you can also find me on social media, but I get so many messages on there that, like, if you write me on LinkedIn or Twitter or something and you don't hear back from me quickly, please don't be offended. I just get so many messages. The easiest way, honestly, to get me is email, because that I do try to make sure I answered everything at least once a day. So if you have any questions, and again, you will get VMs, you'll get the Windows VM too, you'll get the slides and write-ups and everything, and you have info about book 2 that nobody else has. So that's that. That's all we got to today. I appreciate you guys' time. Thank you all. I'm not entirely sure how to give this back.
Thank you, Georgia. Really appreciate you presenting. I think this was a really great starter class for everybody that's looking into getting into doing pen testing. And you really went into depth into a lot of things that I think people are trying to learn and get a handle on. So I
I try.
appreciate that as
I
well.
try to do all the stuff that messed me up when I started.
Yeah, no doubt. So everybody that's in this class probably received an email from me last night as a reminder. I have the list of everybody. As soon as Georgia has this completed, I will email you a link to where you can obtain the VMs. So watch for that email in the next day or two. And thank you again for presenting. Appreciate it.
Yep.
Thank you for having me.
And also, Georgia, just to let you know, you're getting a huge slew of rounds of applause from people in the Discord server. So
Oh, that's
people are really
awesome.
happy with it.
I appreciate it. I get some people who are like, "Oh, you didn't teach me how to hack an iPhone in 2 hours," but I'm glad. I mean, I'm glad people appreciate it. Like, this will take
Yeah, we
you there.
do. We do most of our Q&A through Discord. You're welcome to join the Discord server if you want to. If you want to chat with any of the people that were
Okay.
in your class, it's up to you. I can email you the link to it if I already
Please,
haven't.
that'd be great.
Okay. Okay, we'll do.
All right. Thank
Um,
you.
Thank you.
thank you. I think that's it for the class. We'll see everybody at the next one.